Okay, today we're going to look at how we can create charge on an object and also how to move charge from one object to the other through induction or conduction. So we have three different methods. The first one, friction, is how we can actually create a charge. So friction just basically means something that's rubbing together. So what we're going to do is we're going to rub two objects together, and what will happen is the electrons from the weaker substance, whatever has weaker bonds, those electrons will move to the substance that has a stronger bond. So we've used balloons as an example. So when we rub a rubber balloon on our head, on our hair, what happens is our hair is giving up electrons to the rubber balloon. So that gives the balloon a negative charge, and it would leave our hair as a positive charge. There's two common examples that are often used in physics, and you need to know how these work because they do show up on diplomas. The first one is if we rub a chunk of ebonite, which is just hard black plastic rubber kind of material, and we rub it with some sort of hair or fur, what happens is we get electrons moving. So the idea is just like a balloon in your hair. So the hair particles or the fur particles gives up electrons, and those electrons go to the ebonite. So what happens then is if our electrons are moving, then our fur is left positive, right, because it's lost electrons, and the ebonite will be negative because it's gained electrons. Okay, and if we do the same sort of experiment with a glass rod and a piece of silk, what happens is it works sort of the opposite. So glass ends up giving up the electrons to silk. Okay, so in this case, the same sort of thing. The glass would be left positive and the silk is left negative. So what you need to remember is ebonite will typically be a negatively charged rod if we rub it, and a glass rod will typically be a positive charge when we rub it. So we need to remember those, and a good way to sort of be able to answer these questions and do them is by using this little chart to help you compare. So basically, anything that's higher on this list will gain electrons, and anything lower on the list would lose electrons, so it would be positive. So the things at the bottom of the list would be positive, things that gain electrons at the top would be negative. So if we rub any two of these objects together, you should be able to figure out which one would be positive, which one is negative. So we just did glass with silk, so you can see the silk would be the negatively charged one, the glass would be the positive. When we did fur and ebonite, so the ebonite was higher up, so it was the negatively charged rod, the fur would be positive, and so on. So let's look at this chart and figure out what would happen if we rub copper with silk. So you can see copper is above silk, so the copper would be the negatively charged one, and the silk would be left positive. So it just sort of gives you an idea of how you can use friction to create a charge separation on one object and leave the other one as positive or negative. So now to charge by conduction. A way to remember, think of conduction as being contact. So what we're talking about is touching objects together to transfer charge from one to the other. We talked about it in class if things spark. So you rub your feet on the carpet and you get close to a doorknob. As soon as you get close to it, you'll see a little arc or a spark that'll happen, and you'll feel the shock. We count that as conduction. Even though you technically didn't touch it, if the arc can jump the small distance, we still consider that the same, the transfer of electrons from one object to the other. So let's go through a scenario to see how it actually works. So let's suppose we have a negatively charged rod. So we're going to have a chunk of ebonite, for example. It'll be negatively charged. We're going to move it close to something that's neutrally charged. So we just, in this case, we've got an ebonite rod and a round metal sphere that's uncharged. So what happens is as we get closer and closer, so you can see in this case the thing that was neutral has 3 protons and 3 electrons, but as the negatively charged rod gets closer, it's going to push the electrons away. So we're going to create a charge separation by getting close, but what's going to happen though, once we touch it, it's going to want to balance things out. So don't think of it as being, how many electrons or whatever. Just sort of look at this object as being, just do some simple math. So originally, our first object had a charge of -6. and our other object was neutral, so it has a charge of 0. Once we touch them, 3 of the electrons are going to move over, so we'd end up with -3 for the rod, -3 for the object. Once we move them away, it would stay as -3 and -3. Okay, so conduction, basically what it's going to do is it's going to try to balance things out. Whatever the charges are that are different, it's going to try to balance things out. So we started with 6, we touched them, we got 3 on each. Okay. One thing you got to remember is when we do this, when we charge by conduction, if we start with a negative item going to a neutral object, they're both going to be negative, right? And the reverse would also happen if we started with a positive rod. It's not that the positive is going to move. What we do is we take negatives from the other object. So let's look at that scenario. So that's the example number 2 I'm showing you here. So let's do that one first. So if I had a positively charged rod, so let's suppose it has a +4, and we go to a neutral object, once they touch, we're going to be left with a +2 on each. But what you got to remember is it's not that the positives are moving from one to the other. What would be happening is, to balance things out, it would take 2 electrons the other direction. Right? So we started with +4, so that means we were short 4 electrons. The neutral object had an equal number, so what would happen then is 2 of the electrons would move the opposite direction to try to balance things out, so then both objects would be short 4 electrons, which would leave a net charge of +2. So it's the same answer in terms of math. The only thing that's different is it's the electrons that are moving, not the protons. Okay, what would happen, the first bullet here is what would happen if we had a charge of 7. So let's suppose our original one had -7, and we're going to touch it to something that has 0. So in the previous example we did was we had -6, so after we touched it, it was -3 and -3. So if we use just math, we might say, well, there's going to be -3.5 on each after we touch them. Okay, does that make sense? Well, mathematically it does. Half of -7 would be -3.5, but how do we separate one electron into a half an electron each? You can't. So in that case, what would happen is you wouldn't get -3.5 and -3.5 on each. It would just balance them the best it could, and you'd likely end up with -4 and -3. So 3 of the electrons would move to try to balance it, but you'd end up with 1 extra, and it would just go on one object to the other. Okay, the last one is what would happen if the neutral material was an insulator. So let's go back to the same diagram. So if we had our -7 and we touch it against a rubber ball instead of a metal ball, so if that rubber is an insulator, what's going to happen? Nothing. We touch them together, move it away, it's probably going to still stay at -7 and 0. Okay, so conduction is pretty easy. Just basically remember you're going to balance the charges from before to after. Remember, our conservation of charge still exists. The total is still going to be the same. They're just going to get shifted from one object to the other. Our last one we're going to look at quickly is induction, and this one is pretty cool, and what it is we can actually charge something without actually physically touching it and doing it by conduction. The only key thing is to do induction you have to have a ground. So what that means is we've got a ground wire attached to the object, and what that's going to do is it's going to give us an unlimited supply of electrons to either give or to take. So if we need electrons, it'll take some from the ground. If we have too many, it'll push them down to the ground. And that's what a ground wire does. It just sort of tries to balance things out to make sure things don't get charged up. So the first thing is we're going to do the exact same sort of scenario. We got a metal ball again, but now we're going to attach it to the ground. So you can see in the diagram it just shows it by a little wire that's touched. And usually to show that it's a ground wire, we just do those 2 little lines at the bottom, and that indicates that it's a ground. Okay, so we've got our grounded object. So once again, we're going to bring a -6 charged object towards it. So we've got our rod that's negatively charged, we're going to move it close. So when we did conduction before it touches, what happened was all the negatives would basically try to move away, right? So if we had negatives in the rod, our negatives would get as far away as possible, leaving the side closest to it just positive. Okay, but if they can't go anywhere, that's all you would do. When you move the negative away, it would balance things out again. But in this case, because it's connected to the ground, those negatives, those extra negative charges that are trying to run away, are actually going to go down the wire. So we're going to chase them down the wire, so then basically, however many there are, they're going to be moving down the wire, they're gone. So then all we have to do, without touching it, right, we're just getting close, that'll push the negatives away. We're going to cut the ground wire, so we're going to make a break in the ground wire, so either just disconnect it or physically cut it, whatever the case is. So if we stop the ground, that means all those electrons that were chased down the ground wire can't get back. So now when we pull our rod away, we've lost those electrons. So you can see here in this case, some of the electrons have went down into the ground, but once we cut the wire, those are stuck there, they can't get back up. So now our sphere has a lack of electrons, so that means it'll be positively charged. So one thing to remember with conduction is if we bring a negative charged object to the neutral and we touch it, they're both going to be negative. If we bring a positively charged rod and we touch it, they're both going to be positive. But with induction, it works the other way around. When we bring a negatively charged one close, that chases away the electrons. So once we break that, it's going to be left over as positive. And the reverse would happen if we brought a positively charged rod close. It'll take electrons up the ground wire this time. So then when we move the positive away, we'd have an excess of negatives, so we'd be left with a negative charge. So induction is pretty cool, and I'll try to demonstrate it if I can find the equipment when we're in class. So the last thing we're going to look at is an electroscope, and it's a simple, easy design that was invented many years ago. And what they did was it was basically used to help detect a small amount of charge. Because one electron doesn't have very much charge, it's pretty tough to detect it. We can't feel it, you can't see it, so we have to have a way to actually show that it's there. So an electroscope is just a simple thing where we have this metal rod and it goes inside of a box, usually a round object with a window. And the idea is so that prevents any kind of wind or any excess outside energy affecting it. And it's insulated, so there's a little rubber stopper that stops the charge, of the metal container or whatever affecting anything. And what happens is the very bottom of it has two leaves. And quite often they used gold because gold was a good conductor, and they were really light and thin. So what would happen is if we brought something close to the top, so let's suppose we bring a negatively charged object towards the top, what's going to happen is that'll detect if there's a charge or not by those leaves opening up. So normally they just hang straight down, and as you bring something close to it, the charge then will be detected and you'd see the bottom leaves repel each other, so they'd open up a little bit. So let's look at the bottom diagrams here to sort of look at the different scenarios. So if we bring a negatively charged object to it, that's going to chase the electrons away. So the electrons will go down to the bottom, to the leaves, and because they're both going to be negative on both sides, they're going to repel, so the leaves would open up. And if we brought a positively charged rod, the same thing would happen. We'd bring it close. In this case, it's going to attract all the electrons to the top, so that would leave the leaves at the bottom positive as well. So those would also repel. So an electroscope is good to show the charge, whether it's there or not, but we can't tell whether it's positive or negative. But what we can do is we can also do conduction and induction on it. So if we actually touch the negatively charged rod to the metal, it would balance things out. Then if we moved it away, the leaves would stay open instead of closing again because they've now been negatively charged. So we can do it with positive or negative. And we can actually do it by induction. It's a little bit trickier, but you got to get it close, like one of the first diagrams. You have to get it close to chase the electrons away. Then you have to touch it with another object, another metal rod, while you're still holding it close to pull from the ground or to try to balance things out. Then when you move the rod away, it should still hold a bit of a charge and stay apart, kind of like it did in the last diagram. So conduction and induction, you can get it to work with electroscopes. It's a little trickier, but it will show the effect as well. And that's all.